October 19, 2017. Robert Weryk sits at Haleakala Observatory in Hawaii, scanning routine survey data from Pan-STARRS 1. The telescope exists because NASA's Near-Earth Object Observations program needs to catalog threats, asteroids that might one day intersect Earth's orbit. Weryk finds something else entirely, a dot, 33 million kilometers away, 85 times the distance to the moon, already receding. The object is moving at 26 kilometers per second, outbound. Trajectory reconstruction places its closest approach to the Sun on September 9, 40 days earlier. No one saw it happen. 40 days. A complete perihelion passage, unwitnessed. The initial tag reads, C 2017 U1 Comet. Objects on strange trajectories typically carry ice. They outgas. They develop tails. This one does neither. No coma forms. No dust trail appears. The classification shifts. A 2017 U1 asteroid. Then the orbital mechanics team runs the numbers. The path is hyperbolic, not elliptical, not even parabolic. Hyperbolic means unbound. The object has never orbited the Sun and never will. Its velocity and approach angle point to an origin outside the solar system. The International Astronomical Union convenes. They create a new designation, one that has never existed before. I for Interstellar. 1I, 2017 U1, a taxonomic class invented for a single object, which means that for the entire history of telescopic astronomy, spanning 4 centuries and millions of catalogued bodies, no instrument had ever confirmed that anything from outside the solar system had passed through it. Before the official name is chosen, someone proposes Rama, the alien spacecraft in Arthur C. Clarke's 1973 novel Rendezvous with Rama, discovered under nearly identical circumstances, an interstellar visitor detected too late for meaningful study. The suggestion is declined. What replaces it carries different weight. Oumuamua, Hawaiian. Who, reach out for. Mua, reduplicated. First, in advance of. A scout, a messenger from afar arriving first. The emphasis on first is not metaphor. It is forecast. Statistical models of interstellar object flux suggest that at any given moment, roughly one such object is transiting the inner solar system, meaning Oumuamua was not an anomaly, but the first confirmed member of a continuous, previously invisible population. Observatories across 6 continents redirect their instruments toward the receding point. Karen Meach, leading a team at the Institute for Astronomy in Hawaii, begins photometric analysis. The light curve delivers something unprecedented. Every 7.3 hours, Oumuamua completes one rotation. During each rotation, its brightness shifts by a factor of 10. No asteroid in our solar system does this. No comet either. The only explanation is geometry. An object whose reflected light varies tenfold as it tumbles must possess an extreme aspect ratio, either a needle roughly 10 times longer than it is wide, or a disk so flat it borders on the implausible. Length, up to 400 meters. Composition, possibly metallic, certainly dense. Surface activity, none. Not a single grain of dust surrounds it. The color is reddish, consistent with cosmic ray bombardment across millions, perhaps billions, of years adrift between stars. Dense, silent, tumbling through our system like debris from a collision no one witnessed. Here is what matters. None of this was observed directly. All of it was inferred. The shape, the color, the composition, every conclusion extracted from a point of light smaller than a pixel. You have never seen Oumuamua. No one has. Not a single telescope on Earth or in orbit resolved it as anything more than a dot that brightened and dimmed. Everything we think we know about its form, its surface, its history, calculated from fluctuations in reflected sunlight. So here is the central question: what was it? What do we actually know about the first object ever confirmed to have entered our solar system from interstellar space? And what did we lose when it slipped away? By late October, the data begins to fracture. The trajectory holds. extrasolar origin confirmed. The surface properties hold, inert, reddened, ancient. The acceleration does not hold. Oumuamua is speeding up, not because of solar gravity, it is moving away from the Sunday. Not because of outgassing, there is none. The acceleration is small, persistent, and oriented roughly away from the Sunday. Magnitude, approximately 0.00001 meters per second squared, enough, accumulated over months to shift its position by tens of thousands of kilometers from where gravity alone would place it. Detectable only because multiple observatories tracked it across weeks. Something is pushing it. No instrument can identify what. By early 2018, the question has migrated from observatory break rooms to the pages of peer-reviewed journals. Before addressing the acceleration, consider what Karen Meach's team at the Institute for Astronomy in Hawaii actually measured. The photometry data, gathered across multiple observatories in a coordinated sprint during October and November 2017, revealed a brightness variation unlike anything recorded for a solar system body. Every 7.3 hours, Oumuamua completed one full rotation. During that rotation, its apparent brightness changed by a factor of 10. The ratio implies geometry. A sphere rotating in space shows no brightness variation at all. Every angle reflects roughly the same amount of light. A moderately elongated body, like the asteroid Eros, varies by a factor of roughly 2. Oumuamua varied by 10. To produce such a swing requires an object at least 10 times longer than it is wide, or alternatively, an extraordinarily flat disk, a pancake tumbling end over end through the vacuum. Neither shape has a precedent among the hundreds of thousands of asteroids and comets catalogued in our solar system. Here is the complication that rarely appears in popular accounts. No telescope ever resolved Oumuamua as anything more than a single pixel of light. The elongated reddish rock that populates every article and documentary? Artist's impression. The metallic shard glinting against a star field? Artist's impression. The flat disk catching sunlight at oblique angles? Also an artist's impression. We are reconstructing the geometry of an object 33 million kilometers away from the rhythm of its flickering. The method is sound, light curve inversion is well established in planetary science, but the result carries irreducible ambiguity. Cigar or disk, prolate or oblate. We do not know. We may never know. Meach's team could determine surface composition, at least in broad terms. Spectroscopic analysis showed a reddish hue consistent with organic-rich or iron-rich material exposed to cosmic ray bombardment over millions of years, a process called space weathering that gradually reddens the surfaces of bodies in the outer solar system. This matched expectations for an ancient interstellar traveler. What did not match was the complete absence of volatiles. No water ice sublimating, no carbon monoxide, no carbon dioxide. The surface was inert, dry, baked, and silent. For a body that had just passed within 0.25 AU of the Sun, closer than Mercury's orbit, that silence was notable. Comets at that distance erupt. They shed dust. They grow tails visible to backyard telescopes. Oumuamua did none of this. The classification paradox deepened. Its trajectory, said Comet, only a body from interstellar space would arrive on a hyperbolic orbit with that excess velocity. Its surface, said Asteroid, dense, rocky, devoid of outgassing. Its shape said neither. It occupied a category that did not exist before October 2017. The data resisted every attempt to force it into one that did, and that resistance exposed something more fundamental. Every classification system in planetary science had been constructed from a sample of exactly one stellar system, and Oumuamua was the first data point from outside it. In June 2018, Marco Micheli and a team of collaborators published a paper in Nature that transformed the conversation entirely. Using astrometric data from the Hubble Space Telescope and ground-based observatories, they demonstrated that Oumuamua's trajectory deviated from a purely gravitational path. The deviation was small, on the order of 0.00001 meters per second squared, roughly 100,000th the gravitational pull you feel standing on Earth's surface, but it was persistent, statistically significant, and oriented roughly radially away from the Sunday. In cometary science, non-gravitational acceleration is routine. Comet nuclei heat up near the Sunday. Volatile ices sublimate into jets of gas. Those jets act as tiny rocket engines, nudging the comet off its gravitational trajectory. The Micheli team's data was consistent with this model in direction and magnitude. The explanation should have been straightforward, except the Spitzer Space Telescope had already looked. Infrared observations place strict upper limits on any thermal emission from cometary activity. No dust, no gas, no spectroscopic signature of water, carbon monoxide, or carbon dioxide, the three most common cometary volatiles. Every instrument that could detect outgassing had been pointed at Oumuamua. Every instrument returned the same answer: nothing. The acceleration existed, its cause did not, at least not in any form our instruments could detect. What followed was not confusion, it was a structured divergence of scientific hypotheses, each internally consistent, each carrying implications that ranged from mundane to extraordinary. The first and most conservative, invisible outgassing. Perhaps Oumuamua contained a volatile that sublimated without producing detectable dust or spectral lines. Pure molecular hydrogen ice, proposed by researchers at Yale, fit this criterion. Hydrogen sublimates cleanly, leaving no visible coma. However, hydrogen ice requires formation temperatures below 3 Kelvin. That is colder than almost any environment in the galaxy, outside dense molecular cloud cores, and roughly 270 degrees Celsius colder than the surface of Pluto, the coldest body yet visited by a spacecraft. Whether such an object could survive millions of years of interstellar travel without sublimating entirely remained an open thermodynamic question. The second hypothesis invoked radiation pressure, photons from the sun physically pushing the object. For this to produce the observed acceleration, Oumuamua would need an extraordinarily high ratio of surface area to mass. A solid rock could not achieve this. A thin sheet could. In November 2018, researcher Shmuel Bialy and Harvard astronomer Avi Loeb published a paper in the Astrophysical Journal Letters proposing exactly that. Their model, Oumuamua, was a light sail, an artificial structure less than a millimeter thick, propelled by stellar radiation. The mathematics worked. The geometry was consistent with the pancake interpretation of the light curve. The paper passed peer review and entered the scientific record. This was not speculation dressed as science. It was a falsifiable hypothesis published in a major journal, grounded in the same data available to every other research team. The scientific method does not privilege comfortable conclusions. It privileges conclusions that fit the observations, and the observations, at that moment, permitted an artificial origin. They also permitted a natural one. That was the problem. The data could not distinguish between a hydrogen iceberg, a dust fractal, a nitrogen ice fragment, and a derelict light sail. Every model fit. None could be eliminated. By late 2018, Oumuamua crossed beyond 2 AU from the Sunday. The Hubble Space Telescope captured its final usable observations. The object was dimming, receding, accelerating faintly toward the constellation Pegasus, on a trajectory that would carry it out of the solar system entirely by the mid-2020s. Estimated arrival at the nearest star along its path tens of thousands of years from now. We had possessed a 3-month observation window. Usable data spanned roughly 40 days. Then the first confirmed interstellar object in human history, the Scout, the messenger from afar arriving first, slipped beyond our reach forever. The data was locked. The models were not. In 2023, a team led by Jennifer Bergner at UC Berkeley proposed what they called the simplest explanation yet. Trapped molecular hydrogen, generated by cosmic ray bombardment of water ice over millions of years, could slowly release as the object warmed near the sun, producing a gentle, invisible thrust without any traditional cometary signature, a dark comet, an iceberg that pushes itself with fuel it manufactured passively across interstellar timescales. The hypothesis was elegant, thermodynamically plausible, consistent with every observation. It was also untestable. That single word did not refute the hydrogen outgassing model. It severed it from the scientific method entirely, because the physics held. The thermodynamics were sound. Jennifer Bergner and her colleagues at the University of Chicago had constructed a hypothesis that fit every observation: the acceleration magnitude, the absence of a coma, the reddened surface, the tumbling rotation. What it could not do was submit to verification. The object had already crossed the orbit of Saturn. The data was complete. No additional measurements would arrive, ever. 3 explanations now existed for the most anomalous trajectory ever recorded. Each was internally consistent. Each matched the observational constraints, and each required the others to be false. This is not how science resolves itself. Strip away allegiance. Consider them in sequence. The hydrogen iceberg hypothesis demands that molecular hydrogen freeze into a solid body within a giant molecular cloud, an environment where temperatures fall below 3 Kelvin, colder than the cosmic microwave background itself. Such conditions exist. They are rare, but they exist. Over millions of years, cosmic rays bombard the frozen lattice, embedding energy into the structure. When the object eventually drifts close to a star, the stored hydrogen sublimates, not violently, not visibly, as a slow, invisible exhaust, producing exactly the magnitude of acceleration observed, 5 × 10⁻⁻⁶ meters per second squared. No dust, no coma, no spectral signature detectable at 33 million kilometers. Elegant, thermodynamically plausible. One problem remains: hydrogen ice is fragile. Calculations by Thiem Hoang and Abraham Loeb at the Harvard-Smithsonian Center for Astrophysics demonstrated that a body composed primarily of molecular hydrogen would sublimate entirely during its transit through interstellar space, long before reaching our Sunday. The journey would destroy the messenger before it arrived. The radiation pressure model requires no exotic ice. Published by Shmuel Bialy and Avi Loeb in the Astrophysical Journal Letters in November 2018, the mathematics are direct. If Oumuamua possessed a surface area to mass ratio far higher than any known asteroid, if it were, in effect, a reflective sheet less than a millimeter thick and tens of meters wide, then solar radiation pressure alone could account for the observed acceleration. A tumbling membrane pushed gently by photons. The geometry is extreme. It is not physically impossible. What undermines the model is the tumble itself. A functional light sail, whether engineered or naturally formed, would not rotate chaotically every 7.3 hours. That tumbling motion dissipates the very radiation pressure the model depends upon. An artificial sail would be stabilized. A natural thin sheet would have been torn apart by tidal forces during perihelion, when Oumuamua passed within 0.25 AU of the Sun, closer than Mercury. The third model, catastrophic fragmentation, proposes that Oumuamua is a shard ejected from a larger parent body during a tidal disruption event or planetary collision in another star system. Simulations by Yun Zhang and Douglas Lin, published in Nature Astronomy in 2020, demonstrated that a rocky body torn apart by a star's gravity could produce elongated fragments with aspect ratios approaching 10:1. The shape under this framework is a scar, evidence of violent birth in a foreign system. What this model cannot explain is the acceleration. Rock does not outgas. Fragments do not self-propel, unless the shard contained trapped volatiles, which returns the argument circularly to the hydrogen problem. 3 hypotheses, 3 gaps, 0 capacity for further observation. Then came Borisov. On August 30, 2019, amateur astronomer Gennady Borisov, working from his personal observatory in Crimea with a telescope he built himself, identified a faint object on a hyperbolic trajectory, designated 2I, Borisov, it became the second confirmed interstellar object. Visible coma, detectable outgassing, composition consistent with comets from our own Oort cloud. It behaved exactly as cometary physics predicted, normal in every measurable dimension. The contrast sharpened Oumuamua's strangeness rather than resolving it. If interstellar comets look like Borisov, and they should, given that planetary formation ejects icy bodies into interstellar space routinely, then what produced something like Oumuamua? Statistical models estimate one interstellar object passes through the inner solar system per year. Most go undetected. Too dim, too fast, too distant from any survey telescope's field of view. Pan-STARRS found Oumuamua 40 days late, already departing. We observed it for 11 weeks. We will argue about it for decades. The Vera C. Rubin Observatory, with its 8.4 meter mirror and 3.2 gigapixel camera surveying the entire visible sky every 3 nights, begins full operations in the mid-2020s. Comparison cases will accumulate. The distribution of normal versus anomalous will emerge, but that is future tense. The object that started the conversation is now beyond Neptune's orbit, still accelerating faintly, still unresolved, unless someone proposed going after it. In 2017, before the last photon of reflected sunlight from Oumuamua faded below detection threshold, a team at the Initiative for Interstellar Studies published a feasibility study. They named it after the constellation toward which the object was heading. They called it Project Lyra, and the engineering it required had never been. The answer to what Oumuamua is rests on 40 days of photometric data, a point of light that never resolved into a shape. Project Lyra proposed to close that gap physically. The Initiative for Interstellar Studies published its feasibility study while Oumuamua was still fading from view. The mission architecture centered on a Jupiter gravity assist, slingshotting a compact probe onto an intercept trajectory. Required velocity in excess of 30 kilometers per second. Voyager 1, the fastest human-made object currently in interstellar space, travels at 17 kilometers per second. New Horizons launched at 16.26. Project Lyra demanded nearly twice that. 3 propulsion concepts were evaluated: a solar Oberth maneuver, diving close to the sun to exploit intense gravitational acceleration before firing engines at perihelion, offered the highest delta V. It required heat shielding that does not yet exist at the necessary scale. Nuclear thermal propulsion could deliver sustained thrust, but remains politically and technically constrained. Laser sail propulsion, using ground-based or orbital laser arrays to push an ultralight craft, matched the geometry of the problem. It demanded infrastructure that has not been built. None of these options were impossible. All of them were unfunded. This was the structural failure Oumuamua exposed. Space agencies design missions over 10 to 15-year development cycles. Budgets are allocated a decade before launch. Target selection occurs years before construction begins. Oumuamua arrived without notice, transited the inner solar system in weeks, and departed before a single proposal could clear administrative review. By the time Project Lyra reached publication, the launch window for the earliest viable intercept had already begun to narrow. Each year of delay added roughly 2 years to the transit time. The object crossed Neptune's orbit while the feasibility study was still being peer-reviewed. A direct intercept would have resolved every open question simultaneously. High-resolution imaging would have determined whether the object was an elongated cylinder, a flat disk, or something without analog. Mass spectrometry of surface material would have identified composition, rock, metal, hydrogen, ice, or something unanticipated. Proximity measurements of the acceleration would have distinguished between outgassing thrust, radiation pressure, and mechanisms not yet modeled. 40 days of remote photometry left 3 competing hypotheses alive. A single flyby, even at extreme velocity, would have collapsed them to one. That mission was never launched. The engineering existed at the margins of feasibility. The funding did not exist at all. The institutional architecture of planetary science, methodical, cautious, built for known targets on predictable orbits, had no mechanism to respond to a transient visitor from interstellar space. The failure carried its own kind of data. The Vera C. Rubin Observatory, with first light scheduled for 2025, surveys the entire visible sky every 3 nights at depths pan-stars cannot match. Its detection range for interstellar objects extends months or years earlier in their approach, before perihelion, before the outbound sprint, before the window closes. That extended warning time transforms the problem. With months of advance notice, a pre-designed rapid response mission could launch on an intercept trajectory while the target is still inbound. Project Lyra's architecture, adapted, miniaturized, paired with Rubin's early detection, becomes not a retrospective fantasy but a standing capability. Oumuamua was a natural object. The evidence supports this conclusion without ambiguity. Its reddened surface bore the signature of cosmic ray irradiation across millions of years. Its tumbling 7.3-hour rotation was chaotic rather than stabilized. Its non-gravitational acceleration, while unusual, falls within the range explicable by trapped hydrogen outgassing from ancient water ice. It was not a light sail. It was not a probe. It was a fragment of another solar system, weathered beyond easy classification, passing through ours on a trajectory it will never repeat. What it revealed was not about itself. It revealed that interstellar material transits our neighborhood routinely, that some of it defies clean categorization with remote instruments alone, that our observational infrastructure, built to catalog objects on known orbits, contains a blind spot, precisely where the most scientifically consequential targets appear, fast, faint, and temporary. The Scout delivered its message, not in its composition, but in our inability to read it in time.